Okay, is it on? Is it on? So, it's 9 p.m. in Japan time. I would like to start the live now. The live tutorial for the Houdini today. So this is the 45th episode for Houdini Algorithmic Live, which is a tutorial live for the Houdini that I'm doing weekly for 44 times now, and this is the 45th. And the topic for today is a bit computational geometry oriented stuff, which is to show you how you can unfold a mesh, a given mesh like this, into a flat surface by creating a cutting seam to an edge of a mesh like this. And could be any kind of mesh, like these, or like these. Sometimes it gives you an overlap when you do the unflatting, unfolding. It's due to some curvature of the meshes, so it doesn't work in every and not all the geometry, but for the most of the geometry it seems to work pretty good from what I have tried out. And if it doesn't work, I have also created some random threshold. You can use the random seed here to control the randomness, to change the folding pattern a little bit, so that you can look for the pattern which is not going to overlap. Right, so that's what I would like to show you today. Okay, and it's going to be a tons of vexes again, so if you're into it, that will be great. If you are not into it, maybe it's a bit boring to see. Just a reminder. You can also do a mesh looks like these, which creates this kind of pattern, which is also interesting, I think. With the random threshold, it gives a kind of interesting template. Alright, so let's try to do this in Houdini. Okay, I'll give a new window here. Okay, alright, so I'm gonna start with the really simple geometry, such as sphere. Let's make this polygon, and let's change this to a smooth wire shaded like this. Let's start with this kind of a simple geometry with a small number of faces, so that will be easier to test out. And later on we will change this into a more complex geometry. Now, there is a reference that I have used in order to create this kind of unfolding simulations procedurally, which is this blog here, which is called Houdini Gubbins. And there's a lot of great insight here, great inspiration here about the computational geometry using Houdini. And this guy is explaining the method, how he did using Houdini to unfold the geometry. Well, he hasn't provided the HIP file, but he did kindly enough to provide the algorithm, the method that he used to do the unfolding. So that's what I have followed. So what he did, first of all, build the dual graph auto mesh, meaning he has created a network connecting between the center of the each connected faces like this, and then calculate a spanning tree to minimize cuts and prevent faces from overlapping. So using a spanning tree graph theory related algorithm, he has created this kind of network so that one point there's not going to be any loop for this graph. So there's always an endpoint, and there's no such a loop exist in this graph network. So what he's doing here is that trimming out unnecessary edges to make it a one continuous, or not the continuous, but one connected network, but doesn't have any loops. As a result, you'll be able to unfold the geometry based on this network. You also need to do the rotation using the local transformation information. That's the hard part here. And in terms of using the spanning tree, you also need to set the cost or weight, how much the weight for the edge costs. And it doesn't explain here, but in the comments somewhere around here it says the spanning tree is then computed from the second largest poly, and so on. Not this one. Okay, so you can apply it as a weight function to compute the trees with the smallest but positive added up angle using dihedral angles of the connected triangles. So that's what I followed, and as a result it seems to work pretty good. So I would like to show how I did this. Okay, it's supposed to work for these kind of bunny as well. All right, so let's see how I did that. Okay, so what I'm going to start is by creating a dual network, but you can easily create a dual network using a divide node by checking a compute dual. You will be able to create this kind of dual network easily, but the thing is that it doesn't have any information about each of the point created by this one doesn't have any information about the connection between the polygons, so I'm not going to use this one, but instead I'm just going to do with a wrangle as always, right? So before doing that, I'm going to first make it fused just in case the point is not fused at some point. Okay, and then I am going to calculate the area for each faces so that I can reorder the primitive based on the area. So I'm going to calculate the area, okay, then use the sort node so that the biggest face comes first. So I'm gonna sort the primitive by an attribute by using area. And we'll make this reverse primitive sort and go to the primitive, and you'll see a bunch of areas, and the largest comes first. Now every faces seems to have a really similar areas, so I guess it doesn't really make any difference in this case. Now next I'm going to create a group node, then name this like face. I will use this later to do a filtering. And then I also need the normal direction for each primitive, which I'm going to use to calculate the angle between the neighboring faces, which I'm going to use it for the weights value for the dihedral, the spanning tree. So I need a normal, make this primitive. Oops, let me also save this so that I don't lose the information. Let's name this unfolding. Okay, now what else? Okay, so I think I have enough information to start. So the first thing I'm going to do is to create a spanning tree out of this geometry. And I could start from any geometry, but since I have used the sort to sort out the faces based on the area, I'm going to just pick up the first area, the first face in this geometry spreadsheet, which is this one, as a starting point to create a spanning tree. Now, the spanning tree is a network, which, and in this case, I'm going to use the minimum spanning tree algorithm to create a network. And the thing, how this works, maybe I can explain in a sketch here. Okay, so say you have a, let's see. Okay, this kind of mesh. Say I have this kind of mesh here, and what I'm going to do here is to create some kind of network connecting the center of each faces, but doesn't have a loop, and make the distance, the weight of the edges small as possible. Okay. First thing you need to do is to choose one face to start from. Could be any face, but in my case I'm choosing the biggest face, which has the biggest area. Okay. Now next thing I'm going to do is to, from this point, I'm going to search for the neighboring points, which is either this one, or this one. Okay. And what you need to do is to, in between those three neighboring, I'm going to calculate the weights. Okay, it could sometimes be a length, or it could be an angle between the faces, or it could be any kind of values in order to calculate the weights. In our case, this looks flat, but in our case we have a three-dimensional geometry, so there is an angle between the triangles, so we're going to use this angle, which is called as dihedral angle, which is the if we have a triangle like this, we can calculate this angle here. Okay, so that's what I'm going to use, or maybe this angle here. Okay, and it could be a positive value, or it could be, if it's concave like this, it could be a negative value. Okay, so we're going to use this, I'm going to use this angle as the weight for the spanning tree, and based on this angle I'm going to choose the minimum weight out of these three neighbors, which means I'm going to choose the least angle value out of these threes and choose the first connection like this. Okay, so after doing that, now we have two edges here, 2 points, the 2 endpoints, what I mean. And next thing I'm going to do is doing the same thing, searching for the neighbor for this endpoint, which is either this one or this one, and for this point it's this one. So we have now another three options to check for the minimum weight for the dihedral, and choose, if this one's the minimum, then choose this one. Now we have another 3, so let's say we choose this one. Now this time we have either this one, this point from this endpoint, or this this point from this one, or this one or this one from this point. Okay, and just need to continue calculating the minimum weight until you fill all the faces like this, and without connecting loop. And this is the result of the network that you'll get. And after you have done it, what you're going to do is to cut the edges which does not have any network in between, which means I'm going to cut this part, this edge, which doesn't have a network here. I'm going to cut this one as well, this one as well, this one as well, and I guess that's it. And by doing it, you can make these networks as an individual piece, and as a result you can separate out those, or when you do the unfolding. And in terms of unfolding, you can start from the endpoint of each of the network, for example this one or this one or this one or this one, and then starting to make it flat recursively, one by one. So if you have a face like these, and say this is the end point of the network, first thing you do is to rotate this so that the two plane will be flat. Now after you doing that, go to the next one, then fold everything right here so that it will be flat with this one, and then fold this one again so that it will be flat with this one, and continue doing that. So that's what I did here. I'm not sure how exactly he or she did in the Houdini Gubbins, but this is the way that I'm going to explain today. Okay, hopefully that makes sense. Alright, so starting from making the spanning tree, I am going to use I think I need to do the recursive steps here in order to find out the spanning tree. So I am going to use the attribute wrangle and use it as a detail, since I have to find one by one. If I find one, then I have to find next, and if I find next, then I need to use the latest feedback to find another one. So it needs to be recursive. So I'm going to use detail instead of using point wrangle or primitive wrangle. Okay, so let's see. Let's name this spanning tree righty. Okay, first of all, I am going to create some functions that I'm going to use repeatedly or several times. First of all, to calculate the angle between the faces. Okay, face normals, I mean, or just the normal is fine, I guess. All right. So there's a function that I can use to calculate the triangles, and I have seen it on some paper, the mathematical paper or geometrical paper, how you can calculate the angle between the triangle connected triangles, which you need three informations. One is the edge direction of the connection. In this case, let's say we want to calculate the angle between this triangle and this triangle here. So first information I need is this edge direction, and the second one is the normal of the surface, and the third one is the normal of this triangle. And by having these three, you'll be able to calculate the angle. Okay, so I'm going to create a function called angle from normals. So one is the edge vector, one is the normal 1, I'm gonna say norm 1, and another one is norm 2. Okay, so the equation looks like this. I'm going to just say return. First of all, I'm going to use a ton 2, and inside I'm going to use a dot product for the first input and another dot product for the second input, and inside a dot here for the first one, the first value for the dot will be the cross vector between the norm 1 and norm 2 and the edge. Okay, so which will give you a value in between -1 to +1 in this direction, the projected in this direction, and another dot product between the norm 1 and norm 2, which will give you a projection length between this normal for the surface and normal for the surface. Okay, hello everybody. Alright, so that's the thing here. You can just copy and paste this one as a function, I guess. Now, another information that I need is the point information or point position information, which shares the edges, the shared edge, I mean, between two primitives. So say I want to retrieve the point information for this one and this one, which is creating a shared edge of this primitive and this primitive. I need to look for the half edge information for this primitive and this primitive as well, and see if the half edge is equivalent or not to find out the shared edge. So I'm going to create another function to find out where that is and what's the point information for it, for this one and this one. Okay, so I'm going to create it as a void, including the output parameters. I'm gonna name this get shared edge. Start with the OP input. I might be okay to make it as 0, but let's just make it a bit flexible. And the first information I need is the primitive number for the first one and primitive number for the second one. So int prim1, int prim2. Now, as an exported integer parameter or export parameter, I'm going to create two parameters, one for this point number and one for this point number, or vice versa, this point or this point. Okay, so export int source pt for the first point, export int dst pt for the second point. Okay, now I am going to start by looking for one of the half edge on primitive 1. Let's say this is the primitive 1, and search for one of the half edge from this primitive by, I'm gonna call that half edge number as start by using prim hedge. Okay, and the OP input, which could be 0 if you connect into the first input, and prim1, which will give you the first primitive half edge, which could be either this one, or this one. You don't know yet. Now, since you don't know which one's the first, you need to loop this one. If you're starting from this one, then go to this one next, and go to this one next, and until it can find the shared edge for the primitive 2. Okay, so I am going to create a loop to do the sequence, the search sequence, like this, using for loop, starting from a start, and then hedge is until minus edge is not equal to -1. Okay, I didn't create any incrementation here. That is because I'm doing it inside a for loop. Alright, so and you shouldn't click apply at this moment, which will give you an infinite loop in this case. Now I'm going to create another for loop, name a nh, which is going to be a hedge next equivalent. The hedge next equivalent for the OP input with the hedge, the starting value, which could be this one. So if I have retrieved the half edge information for this primitive, and if it was here, then the edge next equivalent will give you a half edge information for this primitive. Okay, which still leads to this edge here, but which is equivalent to the half edge from this primitive. Now the condition that I'm going to use for this loop is nh is not equal to hedge, and then nh is equal to hedge next equivalent of OP input and h. Okay, it's a bit hard to see here, so I'm going to create a space like this. Is this correct? Okay. Now, inside this one, I'm going to retrieve the primitive number out of this out of this nh, which is the equivalent half edge, and that will be edge prim op input nh. Okay, now what I'm going to do is to check if this primitive is equal to a primitive 2 or not. If it's equal, then you have just found out the shared edge. Okay, if it's something different like this one or this one, then you have to skip to the next half edge. Now, so the condition here is if the primitive is equal to prim2, then I can now get the source point, which is this one and this one. This one for the target, this one for the source. So source pt is equal to edge source point at this nh. So op input nh, or it could also be hedge, or which is this one. Okay, so destination pt is hedge dst point op input nh. Alright, now I can leave the loop at this point. Okay, now if you couldn't find anything for this loop, then what you need to do is to change this half edge number to the next one. If it's right here, then change to this one by using a function called edge next op input edge. Okay, and if the hedge is equal to start, meaning if it comes to the same half edge here by rotating, it starts from here and go here and go here and go back to here. If you have the same values, then just leave the loop. Okay. So that's the function, how this works. Now as a result, you'll be able to feed this source point and destination point information, which it can construct a shared edge like this. Okay, so that was just the function that I wanted to use continuously in order to use it for a spanning tree. Now, having those functions, I can start doing the spanning tree. Okay, now first I'm going to create a variable, the integer variable called order, which is going to be used to define the starting primitive number, and I'm going to start with the 0, which is going to be the face which has the biggest area in this case. Okay, and I am also going to create a array which which could how do I say, which could store all the visited primitive, so that I can skip those. Okay, so to do that, I'm going to create an integer array named as visited. I'm also going to create an integer array which is called as ends, which I'm going to store all the points which can be connected with the neighbors, okay, for the spanning tree. Which similar to the visited, but inside the visited array there is a point included which doesn't have any neighbors anymore to connect. Okay, so for the ends array, I want to only include the points which still have the empty neighbors, connectable neighbors, to make the calculations a bit faster. I mean, you could still use this one, but by referring to the necessary points will give you the calculation a bit slower, so that's kind of a reason why I have two different arrays here. Now, what else? I'm going to also create a point list, which is going to store all the point for the visited center, visited primitive. I mean, I don't really need to create a points to create a network, since I'm just referring to the primitive neighbors. So, and I can just store all the necessary information to each primitive as an attribute, so I don't really need to create any points in this case, but just in case, it's easier to see the connection with the points with the connected line, so I'm also going to create it as a guide. Not really necessary, but we'll do it. Okay, now I'm going to first append some initial value to the visited and ends, which is this order, because we're starting from the first face of first primitive. Do the same for the ends. Okay. Now, I'm also going to retrieve the point information or point position at this first primitive. In this case, let's see where that is. If we show up the number of the faces, let's make the font larger. So this will be the the number 0 face, which is going to be picked as the first primitive. So what I'm going to do now is that I want to pick up the center position of this face. Let's name this as pos prim 0p at order. Okay. Now I'm going to create a new point here, which is going to be used as a guide geometry to create a spanning tree network. Okay, so spt add point 0 as pos. Okay, and let's also set the color for this point. Set point attrib 0 ct to a red. And oops, I need a point number here. It's a bit hard to see what's going on here because this is a closed polygon, so I'm gonna set the shading to a ghosted view, wireframe ghost. Okay, now I see this single point here created. Alright. Now, what else? Okay, so I'm also going to set some initial attribute to this initial primitive, the first primitive here. Okay, so but I also need to append this point into the PTS first. SPT was it? Okay, now's the time to set some primitive attribute for this face. So set prim attrib, and I want to store 3 different attributes to each of the primitive. One is the ID, which starts from 0, and also the previous ID, which shows the connection between the primitive previously created primitive, or previously connected primitive. In this case, we are starting from 0, and there's no previous geometry which is being connected to this one, so I'm going to set the previous ID as -1. Okay, and the third attribute that I want to create is the order, which is this one right here. Okay, which is 0 again. So set prim attribute 0 ID 0 order. Set prim attrib 0 previous ID 0 -1, and set prim attrib 0 order 0 order. Okay, so I guess that's it. Now let's do this. Now let's start by trying it out without going into a recursive iterations. I'm just gonna try with the first connection to find out find out which one will be the next connection. Okay, so to do that, I'm going to start by creating a initial previous ID or primitive number of the previous primitive number, starting from -1, and the next primitive number starting from -1 as well, and the next center position of the primitive starting from 0, 0, 0, and then what else? The primitive previous point. Maybe I don't need this. So I guess these are the things that I need, and also I also need to find out the minimum angle out of this neighbors. So to find out, I'm going to create a minimum angle attribute or variable starting with really big number. It doesn't have to be this big. And I'm going to make this smaller and smaller by if you find any smaller numbers than this one. Okay, by using a condition. Okay, now currently, and what I'm going to do next is to loop through this ends right here. And currently in the ends, I have only one numbers, which is 0, which is this one. So this is the end point right here. And from this end point, I'm going to find out its all the neighbors, which is available as an empty, which available for the connection. So the first thing I'll do is to create the loop inside the orders. I mean the ends. In this case, we only have one. Okay, and pick the primitive number out of this ends. Let's start with, let me use the variable t for this one. It doesn't really have to be t, but, and what I'm gonna do, I mean, since at some point the place where it used to be ends become not is filled with all the connected lines. In that case, we want to remove that point out of this ends array. So if you want to do the remove items inside the array which is used inside the loop of this with this condition like this one, then it's a good idea to start the loop from the end index of the array and goes to the first index like this, so that you don't get it into some weird loop. After you removed it, then the size will change, so this loop will give you a weird error if you start from 0. So it's a good idea to start from the end. if you want to remove the item inside the ends array. Okay. And where was I? So I have retrieved the primitive number. Now I would like to retrieve the center point position of this primitive by using a prim 0 p at prim. Okay, and also would like to retrieve the normal direction of this primitive, which is going to be used to calculate the angle, one of the information that I need to calculate the angle between the neighbor primitive. So vector norm1 is prim 0 n at prim. Okay. Now, next thing I'm going to do is to retrieve all the neighbor primitives from this current primitive. And you can do that by using a function called polyneighbors. Polyneighbors 0 prim. Okay, so now you have a neighbor primitive array, which in this case should be 3. You should be able to get 3 primitive neighbor numbers, right? Now I am going to loop through all these. Like this one. Oops, I seem to have some errors somewhere. Okay, it says, okay, I need to change this to T here. Right. Okay, so I'm going to retrieve the neighbor information out of this array. Okay. Now, what I want to do now is to check if this neighbor has been used already as a connection or not. Okay. To do that, we can go to this. We can check if the value or neighbor number is included inside is visited, which is to check whether the point has or primitive has been visited or not. If you couldn't find it, then you're good to go. Okay. So I'll use a if condition with the find. If this neighbor number is included in the inside this visited array. If it's negative, then it's not included, so you're good to go. So in that case, I'm going to retrieve, if let's say this is the neighbor that I'm going to look at, I'm first going to retrieve the center point position of this primitive, which is prim. By the way, do I need that information? I guess I do in order to add the point. Yeah. So prim 0 p neighbor, and also the normal. So I'm gonna name this normal norm2 prim 0 n neighbor. Okay. Now I can, at this point I can calculate the angle between the two primitive. Now to do that, we also need this shared edge direction. So to retrieve that, we need to use the function that I've created, which is this one, to get the shared edge direction right here. So I'm going to retrieve this one and call it right here, and we need an OP input, primitive 1 number, primitive 2 number, and output parameter for the source point and destination point. So I'm going to create a source point and destination point as an empty variable and use get shared edge 0 for the first input, and primitive 1 is in this case prim. So prim, and the neighboring primitive number is in this case nay. So nay, and source pt for the output and destination pt for the output, another output. Okay, now out of these point number we will be able to get the point position as well. So source position is at pt, and vector destination position is 0.0 p destination pt. Okay, now out of these 2 point position, which is in the shared which is on the shared edge, one position right here, one position right here, we'll be able to calculate the direction of the edge, which is I'm gonna call this name edge direction is normalized destination position minus source position. Okay, now now that I have enough information to calculate the angle between 2 primitives, one is this edge direction, one is the normal one, and one is normal 2. So using the function that I have created, I can calculate the angle, which is angle from normals, and one is edge direction, which is the edge direction, and the norm 1 and norm 2. Now the angle that you get out of this function is in between minus pi to positive pi, okay? And negative means, in this case, I think it means concave, or yeah, concave. But I want to have this convex angle to be negative. Or is that the case? I think. So what I'm going to do is to calculate this angle. First of all, I'm going to have pi and do the subtraction with this angle that I've calculated right here. I'm doing this because it seems to work well. So this angle will be used for the weight for the spanning tree, which is going to be used to calculate the weights between the neighbor primitive. Okay. And if this angle value is small, then you tend to have more possibilities between those primitive. Okay. That's the rule here. So if the minimum angle, which I've created right here, is bigger than the angle that I've just calculated, then feed in this minimum angle with the current angle, then choose all the feed all these variables with any necessary information. So the prev is filled with a primitive number. So for this neighborhood polygon, the previous primitive number is going to be this one, with which shows the connection. Okay, so this is and the prim is currently this one, and prev for this primitive has to be this one, so filled in like this one, and the next is this neighbor primitive numbers, so in this case nay. Okay, and then I am going to feed in the next position as well, which is going to be npos, which was this one right here. Okay, and the prev, I guess that's it. Okay, so I think that's pretty much it in order to fill in. Now, you can go with this, but I found out that sometimes this minimum spanning tree will give you an overlaps when you unfold it into a flat surface due to a choice of this minimum angle that I have used for the cost calculation, the weight calculation. So, and I found that having some random values together with this minimum angle will give you a bunch of choices that you can choose from the for the best choices which doesn't overlap when it unfolds. So I'm going to create additional conditions here using a random value. Okay, so I'm going to say and inside here I'm going to create a random function to create a float value in between 0 to 1 using, in this case, t and I as a seed value, so t multiplied by some constant value, could be any value, and I multiplied by some constant value as well, and plus some parameters that you can change by yourself. So I'm gonna name this seed. Okay, and apply. Oops. Okay, it might be related to some min and, okay, some spell mistake somewhere. Okay, I guess this one, ming ang. Right. Now, now I need a condition for this random value that I've just created. So somewhere around here, I'm going to create another parameter to control the threshold. Okay, so if this threshold is equal to 1, then this condition will always equal to true. If it's 0.5, if this is 0.5, then half of the 50% of the possibilities this condition runs. Even if the angle meets with this condition, 50% of the possibility it doesn't go to this, doesn't run this operations inside. So this kind of condition will give you a chance to ignore some of the best choices and look for the other possibilities. Now, but there's a problem here, because if this random values, this threshold is really small, like 0.1 or 0, then it never gets, this condition never will be able to operate the one that's inside, and that's a problematic because we do need to have some kind of value for the later operations. We cannot have -1 for the primitive or next. So, and we need to feed in at least 1, even if you couldn't find any conditions here. So, what I'm going to do is to create another condition here using OR for the rand value. If the random value is smaller than the threshold, or what I could do is to just choose the first item that I have found using a count value, maybe how many times this primitive, or how many times the operation has been done or not. Okay, so to do that we need to have some variable named as something like ncount start from 0, and maybe we could increment this ncount somewhere around here inside the second for loop, and we can say if the ncount is equal to 0, then we could we could forcibly run this how do I say, the insertion operation. Okay, so that's kind of a trick here. Okay, so I'm going to check if there's no errors. I think that's fine. Now I'm going to promote those two parameters, one for the seed and one for the threshold. I'm going to keep the threshold as 1 for now, so that every step, the minimum angle, the most smallest angle will be used as a weight without using random for the initial test. Okay, everything looks good at this point. Now we also need to remove the unnecessary primitive information from the ends and also from the point list, which is not if there's no neighbors available anymore. Okay, so the condition to find out if there's no neighbors is by looking at this ncount case and looking for this loop here. So if the ncount is not being incremented, meaning if this operation didn't run, meaning this condition right here didn't run, or this loop, meaning there were no available neighbors for this primitive that I've chosen here. So if you couldn't find any available primitive, then you can just stop, or I mean you can remove this very point that you have. So if the ncount is equal to 0, meaning if you couldn't find any neighbors, then you can remove index and add in this case t, and same for the point ptst. Now it starts to get a bit complex here, but we are almost, not almost, but we have just created the necessary information here. Now we need to do another kind of loop here. After we have done all these calculations here, what we get as a result is this primitive previous number, previous primitive number, and the next primitive number. Okay, so, and also some next point position as well, which is just side information. Now, having all these information, we're going to check if the next is larger than 0. If it's negative, then it's time to stop the whole loop, because it means you couldn't find any neighbors, meaning all the faces has been connected with the network. So that's the time when you want to stop the loop. Hello everybody. Okay, so first of all, if you find a next, then first thing you want to do is to append the visited with the next primitive number, and also append the ends with the next. Okay, and then I'm going to create a new point at this center. It could be this primitive or this primitive or this primitive. So int next pt is equal to add point 0 next position. Let's also set the color. So set point attrib 0 cd at next pt as set 100, so that will be red. Okay, so that it seems to be this one. This primitive was chosen for the next connection. Now I am going to append this next pt to the pts. So pts next pt. Okay. Now, what I'm going to do next is to create a line connection so that I can see how the network is being created. So, int line and add prim 0 polyline between the next pt. I also need the previous point number, and I guess I didn't create that, did I? I guess I need that information as well, so I'm going to create another variable here, int prev pt start from -1, and go back to where I have find a -1, and there you can set this previous point number with let's say in this case the last point or current point number inside a PTS. So it could be like this. Okay, now go back here and connect the next point number and the previous point number. We'll create a line like this. Maybe I should use the shading with the wireframe. Okay, now it's more clear. Okay, so now I have just created a first connection. It's going to be faster now. Alright, so next thing I am going to do is to what I'm going to do next is to apply a for this or maybe this one, for this primitive, for this neighbor primitive that I have just found out, I would like to apply a attribute that I'm going to use to unfold later on using rotation, which is going to be this axis information and the point position of the source and the destination. Okay, which can be retrieved using the same function that I've created here, get shared edge, between the previous primitive and the next primitive. Okay, so again, I'm going to create a source pt and destination pt and get shared, what was the name? Get shared edge. Just gonna copy these. Oops. Get shared edge and start from 0. And what was the second parameter? So primitive 1 will be, in this case, a prev. The next, I guess that's right? Okay, and the source point, source pt, and the destination pt as export output parameter. Now you can retrieve the position for the starting point Source position. It says why you are not using an external ID for Vex. What is I'm not sure what you mean by external ID. You mean IDE? Well, it just gives you these guides, so I guess that's the reason. Maybe using Visual Studio Code makes it be easier, but I'm frequently change the version of the Houdini, so changing the direction, changing the destination to the ID is just kind of cumbersome to me. That's the reason. Okay, so vector source position is 0.0 p source pt vector destination position point, oops, right here, 0 p destination pt. Okay, now I can also calculate the vector axis. Okay, so that's going to be vector edge direction is a normalized of a destination position minus source position. Okay, and also I would like to calculate the angle as well, so apply to this primitive so that I can use it how much I should rotate. So the angle again can be retrieved using this function that I've created. So go this one. So to do that, we also need a normal direction of each of the primitive, so let's retrieve that as well. So vector norm1 is a prim 0 n at prev. Vector norm2 is prim 0 n next. Okay, now the angle that I would like is a angle from normals edge direction, norm1, norm2. Alright, so now I have enough information to use it for the attribute. So finally I'm going to use set prim attriv to named as, first of all, edge position 1 for the next primitive with the source position, and for the destination position I'm going to name it as edge position 2 dst position, and I'm going to create a edge axis. I'm going to use this for the rotational axis, which is going to be edge direction, and also we need the angle, so edge angle is this one. Okay, and what else? What else? Okay, I guess that's pretty much it, is it? Now, okay, well, I also need some information whether this to this edge group right here. So this edge group should not be cut since it is being connected right here. So I would like to set some edge group to determine that this edge should not be cut later on. So I can do the set edge group, and let's name this keep in between the source point and the destination point, set as 1. Okay, so I guess that's pretty much it that I need to do in order to set necessary information, I think. Let me see. I think so. Now, if I have done it correctly, then what I need to do now is let me check. So I have just applied those primitive attributes. Now let's see, apply, accept. So I have just created single connections between two primitive. And see, let's look at the primitive geometry wrangle. See if it has been created correctly. I'm going to check the... Okay, I think I didn't set the ID or the order, so I think I need to do that. Okay, the previous ID is not set as well, so we need to do that. If I check the edge angle, okay, so at some point there is an angle here, and it should have an ID being applied, and the order has been applied as well. So let's do that. Okay, and where does it should be? Okay, going back and see where it should be. I think it should be somewhere close to right here. Okay, so set prim attriv 0 ID, which is going to be the current ID, which will be I'm just gonna use next. Okay, and I am also going to set the current order for this one, but the order has to be incremented by 1 at some point, I think. Now where can I do that? Let me check. I think inside this condition somewhere I should increment the order, so maybe I could say somewhere like this. So the order incremented by 1 every time. The next, the one that I have applied here, the ID is equivalent to the primitive number here. And set prim attriv 0 prev ID is equivalent to the previous primitive number. Okay, so I also need to set the order as well. So set prim attriv 0 order, next order. Okay, so if I look at the geometry spreadsheet, now I have the order 1. If I look at the previous ID in the order, now it says the previous ID is equal to 0. I think that's correct, and the current ID is equal to 24, which should be the number for this face here. So if I show up the number for the face here, it says 24, so okay, that's correct. And all the information here, the edge axis, edge position 1, edge position 2 is related to this edge here. Okay, we cannot check the edge group in this geometry spreadsheet, unfortunately, but should be applied. Okay, and the edge angle shows the angle between this triangle, which is going to be used to which is going to be used later on for the rotation. Okay, so I think all the necessary information has been applied for the first connection. Now what I'm going to do is to do this operation recursively, repeatedly, by using the last information. Okay. Now to do that, what I'm going to do is to wrap up all the functions that I've written so far for the first connection and repeatedly doing it over and over again until it fills all the faces. And we can determine how many loops we need to do because we know that the number of connections is equivalent to the number of faces. You see? So what I need to do is to create a loop, another loop somewhere around here. It's named in variable n equal to 0, and n is less than n primitives group, 0 face. The reason why I'm using n in primitive groups is because there's a line primitive here, so I don't want to use it for the count. And so I only want to calculate the face numbers here. Now go back and close the loop like this. And where is it? Right here. Okay, now inside the loop I need to feed back some of the information, I think, which is related to this n value here. So let's see where I should use that. But I guess I don't really need to, because the things that I'm feeding is these n's and visited, and I'm already doing it right here, so it should work. Okay, here we go. So it have just created a spanning tree network like these. Can you see it? Yeah, it seems to work well. Now, yeah, I think that looks fine. Now, if I change the geometry's frequency, let's see if it still works. So 3, 4, 5 looks fine. Okay, well, everybody is suggesting me to use ID. I don't really want to though, but if I need to, I can use this. Okay, this leads to the text edit. Maybe I can use Sublime sometime, but not today, sorry. Okay. Now I think the spanning tree seems to looks good. Now what I want to do is to try changing those seed values or the threshold values and see if I can change these networks, the types of randomness. So let's make the frequency smaller and show the wireframe and see if we can. And let me also pick up only those network by deleting the faces. Okay, now these are the networks that I've just created. And if I change this seed, okay, you can see that the network connection is changing. It still use a minimum angle as a weight, but at the same time using some randomness to skip some of the angle, which will create some variety of choices. If you keep this threshold to 1, then there is no more variation available because there's no randomness used if the threshold is equal to 1. If it's 0, then everything becomes random. So that's not a good choice as well. I guess it's a good idea to keep somewhere in between 0.5 to, I mean, larger than 0, but maybe 0.1 to 1. Gonna keep this to 1 for now, because I want to see how the least minimum weight will look like when we unfold it. Now, as I said, this edge information that I've created is just a guide, so I don't really need these. So instead of deleting face, I'm going to delete those edge. Okay. Now, next thing I would like to do is to cut the unnecessary edges, meaning where the network doesn't cross. So as I said, if there's a connection between the primitive, I don't want to cut in between this primitive. But if there's no connection, then there's the place where you want to cut and using for the unfold. Okay, so to do that, I'm going to use a edge cusp using edge group. Now we have used the keep group to determine which edge to keep, so using a apostrophe with the keep, you can cut all the face which is not set with the keep group. So let's show this up in the shaded view, and currently it looks like this. And if I turn this on, you see some cusp starting to appear at some of the edges, and that's where the the connection has been deleted between two primitive. So I think it becomes fine. So in order to check if the cusp really worked, I can pick one of the points and move this. Okay, maybe not here. Okay, has to be after this. Okay, so there's a openness right here, and that's where the connection is not being made, I think. Yeah, so there were no connection between those primitives, so that's where we have these spaces. Okay, so it looks like it's working. Now that I have created the spanning tree network information, it's time to unfold the geometry using some rotational matrix or rotational operations. Okay, so what we need to do is kind of do it recursively again from the end point of the network. Meaning, if we look at these network information right here, it's a good idea to start from the edge of the network and unfold it one by one. Now, to choose the end, it's a good idea to use the value that I have created, which is called as order for the primitive. So in this case, I have created this order attributes right here, and this indicates the when the geometry, or when the primitive has been created. Okay, when the face or being connected, I mean. So meaning the last connected piece should always be the endpoint, right? So meaning we could start from the end order and go to the negative numbers. I mean, to the go to the descending order from 179 to 0, so that we could always use the we could always start from the children, the very children of the network, to the parent. So the order equal to 0 is the parent, the grandfather of this tree network, the spanning tree network. Okay, so that's what I want to do. So what I'm going to do is to use the sort to sort out this primitive based on the order. So change this to by an attribute, set the order attribute and reverse, so that the primitive number will be realigned, rearranged using the order attribute. So it starts from the biggest number to the smallest number, like this. Okay, and I'm going to do the unfolding from the first primitive. Okay, now going back to a sketch, what I'm going to do now, let's say we have a something like this. Okay, and let's say this is the parent. This is the parent face, and this is the children, which I'm going to start with when the order is the biggest. Okay, so let's start. Let's say this is 1. And the first thing I'm going to do is to retrieve from this children, there's a attribute that I have applied, which is the angle of between these triangle, which is set as theta. Let's say it's set as theta. If you look from the side view, let's say this is the C, this is the neighbored primitive. What we have is the angle right here. So easy for the first one, we just need to use this edge as an axis. We also have an axis information applied, so we can use the axis information together with the pivot of the rotation to rotate this face by this angle here, so that it will be flat to the next primitive. Okay, so that's the first thing you need to do. Now in the next step, let's say this is the second largest order one, so C2, C1 and C2. Now for the C2, the neighbor or the previous primitive for this one will be this primitive, right? Which is connected to this one. So we have another connection to a, let's say this could be C3. And we have another angle here, like this. So what we need to do is to do the similar things that I did here for the C2. But what's important here, that when we rotate, I guess in this case we need to rotate the C2, so we need to use this angle here. Okay, so we need to rotate the C2 like this, but when we do the rotation for C2, we also want to rotate the children of this C2 as well. So we pick all the children which connects to this C2 and rotate the whole set, the whole branches like this, including C2 and C1. Okay, and that's what I need to do recursively, one by one. We need when we do the rotation, we first need to find out the children from these one that I want to rotate. Pick all the children and rotate all the children all together using the new axis, the new rotation axis with an angle. And same for the C3 and other geometry. Okay, which is the transformation that I'm going to do today. So well, last week it was more simple because there's just a single rotation. But in today we have like connected, chained rotations, so we need to do this kind of bit complex stuff, bit complex transformation. And I am going to, since I'm going to need to do this recursively again, I am going to use another attribute wrangle, but I am also going to use the for each loop as well, so for some reasons. Kind of a need how do I say the it's more easier to, in this case it's more easier to use this for each loop back feedback loop to do the recursive. I mean, normally if in other programming languages like C++ or C#, you'll be able to create a recursive function, but in Vex you cannot do that because it's based on the simultaneous process. It's more like based on the shader language. So it doesn't allow you to write the recursive functions. So instead what you could do is to use a combination between the for each and the wrangle. So it might looks a bit complex, but it works just fine. Now let's name this as base connect it right here. Now it's time to play. So I am going to create another attribute wrangle, which will going to be the last long code that I'm going to write today. Okay, like this, and let's name this unfold. Okay, let's set it to detail, and for testing I'm going to set the iterations to really low so that I don't get it into some weird crash. And I'm going to change this to feedback each iteration, and then go back to the for each begin and change this to fetch feedback so that the loop will become a feedback loop. Okay, now for the unfold, maybe I can start with the 1 just in case. Now for the unfold, let's do some coding here. I would need first of all I need an information what's the iteration number currently, and be used to retrieve the next primitive based on the order. So I'm going to retrieve the detail attribute, call iterations from the second input. I'm gonna call this as I detail 1 iteration and stop. And it starts from 0 and counted up by incremented by 1. And I'm going to use this number to pick the primitive out of this input right here. And currently we have 180 primitive, so by using 0 as a first value for the first iterations, you'll get the first primitive out of this geometry spreadsheet, which has the highest order, which means it's in the which is the network node created and the very last. So meaning that's the grandchildren of the network. All right. So going back to the code, where was I? So I have just retrieved the iteration or the primitive number. What I'm going to do is to retrieve several attributes from this primitive. So first of all, ID. So ID at I and vector edge axis prim0 edge axis I vector edge position 1 prim0 edge position 1. Now we have position 2 as well. We might not need that though, well, just in case. And the angle, so edge angle, so prim0 edge angle I. Okay, now what we can do now is first of all, we need to retrieve the total number of primitive, the array of primitive numbers to pick all the children that we need to rotate in this iteration I. So if the I is equal to 0, that's fine. There's only one primitive that you need to rotate, but when the I gets bigger and bigger and the order is at somewhere around here, then there's going to be tons of children connected to this one, and you need to find all the children recursively as well. Okay, so we need to have a list to manage the total list to manage all the numbers that we need to rotate, all the primitive numbers to rotate. So I'm gonna name this as total next nums, starting with a I. I is the one that should be rotated in the first place. Now from this primitive I, we're going to find out all the children connected to this one. Okay. And I am also going to create a temporal array named as next nums, which is going to be used inside for the recursive function or recursive loop. Okay, and and I would like to, okay, I think I need to get another information which is called prev ID from the primitive prev ID. Okay, so the previous ID, if you got the previous ID from the primitives, you'll be able to, if you, let's say this is the primitive that we are looking at right now and it's connected, the connections being made from this one, then the previous ID will be leads to this primitive number here. Okay. Okay, so that's the information that we have currently. Now we can do the loop. Maybe we could. And the first thing we need to do is to find out all the children recursively. Okay, so I'm going to name as t. T is less than. So there is a chance that one single primitive has all the possible faces as a children. So the maximum of this loop could be a total number of the face. So n prim fibs group 0 face t++. Okay, but most of the cases it's not it's much smaller than the total number of the faces, so we also need to have some functions to break or stop this loop with some conditions. I'll do that later. Now I am going to first retrieve the total number of the total next nums, which is going to be used for the condition to stop this loop later. And I'm also going to create a temporal total temporal array to store all the found previous children point numbers, which is going to be updated recursively. So total t next nums, starting with the empty array. Now it's different from the one right here. I just added this t as a meaning for the temporal. Okay, so I'm gonna create another for loop using s. S is smaller than length of next nums. Okay. And the next nums, we currently have this array as equal to I. And this next num is also going to be updated recursively. Now, what I want to do now is to check the next number, I mean the ID of at this I here. So int. So I'm just going to retrieve the next number out of this array, which initially is just this I value, which is started from 0. Okay. Now from this one, I'm going to retrieve the ID. Okay. And use this ID to find the possible previous ID. Now there is a chance that you have multiple children, from this ID. Let's say this one is the one that you're looking at, but for this one, maybe you have this one and this primitive as a children. So meaning you might have 2 or 3 children. So we need to first count how many children we have using a find attriv find attriv bulk count 0 and primitive class and look for the previous ID. Okay, so and with the current ID. So if what I'm doing here is to check all the faces and see where it has a priv ID which is equal to this ID, which means by doing it you'll be able to find out the children by using ID as a search filter or query. Now this one just gives you an account how many numbers of children you have, and as a result you can set you have just created the number which can be used to see how many loops you need to do. Okay, and at this point I'm going to create another temporal array which is going to be used for the next num. So I'm going to name this t next nums array Now it's going to be more complex here. Now I'm gonna do another loop. N is equal to 0, and n is smaller than p count, which is this one. And look for all the neighbors, or all the children that has been found. So int next num is find attriv val 0 prim rev id and id with an, so that you can check all the children one by one. In this case, using this value, this function together with this value, you can find all the children. Okay, now I need to check if the children is the children number is more than 0. If it's negative, then we cannot use that. Okay, so if it's positive, then we can now append the, first of all, total next nums with the n next num. The total next nums have all the found pieces or found children that we need to rotate all together. Okay, and also we need to append the t next nums with the same number that I found, which is going to be used later on for the after we leaving this loop. By having all these numbers, the temporal numbers being applied, I'm also going to append the total t next nums with t next nums that I've just created here. So what I'm doing here is I have created an empty array here, and each time for this face t equal to some numbers, for some of the face I'm creating all those numbers being applied to an empty array which I've created here and stored it into this total t next nums. Okay, so this array indicates the number of children found for a specific face, not for all the face, but just for a specific face. Okay, now that we have feeding all the necessary information, what I want to do next is to check if this total number of count, which is equal to tc, total number of faces was tc, was it or not? Okay, so the tc was the total number of the next nums, is equal to a total the length of total number of next nums. So what I'm doing here is to check if the number has been changed using these operation. So the tc was previously set, and by using this loop, if anything is added to the total next nums array using this function, then you can continue doing the loop. But if you couldn't find any change here, if nothing has been added, then that means there's no more children you could find for the connection, for the rotation. So that means that's where you want to stop the loop. Okay, now and last, for the next loop, when t was equal to 0, we were looking for the first phase, but for the next loop we're going to use this total t next nums as a next group to search for the children. Previously we have used this one, this next nums for the first set to search for the children, and the next loop we're going to use this one for the set to search the children from. So we just, what I'm going to do is to replace this next nums with a total t next nums. Oops. Okay, some errors somewhere. Let me see. 36. Nope. Invalid source sphere and fold attribute. Okay, I guess something is wrong somewhere. Let me comment this out. See if this works. Okay. And bring this back. And let's check whether this function or loop works. Okay, so somewhere around here. Int total t next nums is equal to empty array in tc's length total next nums. Looks fine. Okay, if tc is equal to length of total, okay, next nums. Okay, now it looks good. Alright. Oops. Total next nums. Maybe I have some other t next nums. Let me comment these out. Okay. Spell mistake again. Okay, so that looks good. So as a result, I should be able to feeding all the children information into this total next nums. Okay, so let's check that out, shall we? So I'm gonna create a array, integer array named as a, just to check this total next number that has been fed recursively. Now let's see what it says. Now it says 0 because there's only one feedback loop here. So if I set it to 2, now we have 1 0, and if we increase this to some more, we can see more values being added. Okay, so I guess it's working. So let's see. Starting with 1, I'm going to try to do a single rotation now for the single face, just to test out. Okay, so now it's pretty easy to do. I'm going to loop through all the numbers from this total next nums. What I need to do is to do the same rotation operations for each of the primitives points. So int t is equal to 0 and t is less than length of the total next nums t, and int next num is equal to total next nums at t. Okay, and then we can retrieve all the points from this primitive, so using prim points at next num. Now we can loop through all these points, and what I want to do is to rotate each of the points using the information that I've retrieved from the primitive, which is these. Okay, now first of all we need to rotate the positions, point positions, so we need to retrieve the point position from each of the point numbers. So let's name this npos is equal to 0.0p at pts. And now I'm going to create a rotational matrix. And ident mat, and the angle that I want to rotate here to make it flat is this angle that I've retrieved from the primitive. So edge axis as an angle right here. Okay, now I have just created the rotational matrix. What I can do is to use this to rotate the point, but before doing that I also want to move the point to the pivot location, which is this, which could be this one or this one. Either one is fine, I think. So I'm gonna use this one, edge post 1. So to do that, first of all I'm going to subtract or move back to this point that I have found here with the edge position 1, and then apply the matrix, the rotation matrix, then move this back to the pivot location. Right, and then to be able to see which one has been rotated, maybe I can set some color information to this one. Or before doing that, we need to update the point position. So set point at riv 0p at pts n with a npos. Okay, and let's also change the color. So set point at riv 0 cd pts n with maybe green. Could be anyone, could be anything, just to test. So where is it? Okay, here we go. So okay, I think it's rotating the other way, so I guess I need to make the angle negative for this one. If I make it negative, okay, now it becomes flat. So for the single face it worked. Now let's see if it's going to work for if I increase this feedback loop. If I set it to 2, you can see that the second last face has been rotated together with this children. If I set it to 3, now it's rotating again. It's like peeling the orange like this. And if you actually the total number of iterations you need to have is the total number of the face minus 1. The last one, the grandfather of the network doesn't have to be rotated, so, and it doesn't have the previous information. So it's actually the total number of the iteration in this case is the total number of the faces minus 1. Okay, so we can retrieve this as an expression using n prims group from maybe base, and the name of the group is face -1. And as a result, I have just rotated everything to make it flat. Alright. Now, currently it's rotating like 100% from the original geometry to a flat surface. To make it like to be able to create an animation to open up from the sphere to this flat surface, what you could do is to multiply some values in between 0 to 1 to the total angle, which is this one right here. So I can create a parameter, let's say ang_mult as a float number. Okay, starting from 1, and if I increase this value slowly, you can open up the face like this. Alright. Now it depends on the face you pick, it will it does create a flat surface, but the orientation of the surface is not faced, or it's not placed on XZ plane or XY plane or any plane. So if you want to align this to a XZ plane, like for example, what you could do is to create another point wrangle and also connect this base to the second input. Since the first primitive is not going to be, the first picked primitive is not going to be rotated, okay, so the first primitive's normal direction is going to be used as the orientation of this surface. So we could pick the normal of the first primitive and known prim first I mean the second input 0, and I can use this to create an orientation matrix, matrix 3 mat equal dihedral between the from this normal of the primitive to set 0, 1, 0. So all the face will be facing upward in this case by using this matrix. Now I can multiply this matrix to all the points, and then oops, something happened. Okay, something might not be correct. Okay, I might need to create a normal for the normal primitive. Okay, I think I'm missing something here. Let me check. I might need to connect not this space, but before sorting out, I think. So somewhere around here. Okay, so let's connect this one right here. Okay, now it seems to do the job. Now it's on flat surface, I mean a flat XZ plane. And if I move this angle, alright. Now I don't want to see this ghost view, so let's create a null controller to store the parameter that I want to control. Let's call it this up. And the parameter that I want to control is the angle. Unfold the angle, I guess. Unfold angle. Unfold angle from 0 to 1 copy this, paste it right here. Now I can, oops, gotta make it as a float. Alright, looks good, isn't it? Now it's time to test out those random related values. Currently there's no randomness applied for this one, so it's only using the the minimum, the minimum angle value as a weight control, the weight value. Though if I increase the frequency of this sphere, at some point you might see some overlap. Oops, that might be too big. Okay, let me set this to 5 and let's see if there's some overlap somewhere. Yeah, something like this. At some point you might be able to see this kind of overlaps, like this one, even if you use the minimum angle as the edge, the weight value for the spanning tree. So and in order to see other variations to check for the parts which doesn't overlaps, then that's where I can use these random related values. So I'm gonna store these values as well to this controller. I'm going to, and for a bit linking, and then go back to this one and see it, seed and thresh. Let's bring this up. The first one, I'm gonna name this rand seed. The second one, I'm gonna set land thresh. Okay, now let's check this out. I'm first going to set the threshold to something like 0.5. So 0.5 and see. Okay, there is still an overlap, so if I change the random seed, you might still see some overlaps here. So you can keep changing it until you find any no overlaps, or you can also make this random threshold smaller to make it more randomish network. Maybe if I set it to 0, it might, well, it does a little bit. It does have a little bit of overlaps. We might be able to ignore it. Maybe not for this one. Well, that's how you can look for the stuff which doesn't overlaps. Maybe by using this parameter with another feedback loop, you can search for the one that doesn't overlaps. But that's gonna make the whole steps really slow, I guess, so I'm not gonna do that. If you want to do that by yourself, feel free to do that. Okay, but overall that looks good. Now let's try to see other kind of geometries. And now let's, first of all, I'm going to try with the torus. Okay, and see how this works. Okay, so I'm going to create a switch node so that I can switch between geometries. And go back here. And let's also create a switch parameter. say from 0 to 10. Okay, and for 0, I'm gonna copy this value to here. Right. And let's change this to 1. Now this is the result of the template or the unfolding for the torus, which looks a bit irregular. That is because I'm having this random value applied. Now if I set this random threshold to 1, then no random will be used. Then it will create as this kind of a regular looks shape, which looks okay. Okay, well, it's not that interesting, is it? Now, next thing I would like to try out is a bit more complex stuff. Maybe we could use some test geometry, like let's say test. Let's see, we could use like a temporary body. Okay, it's facing. That's funny. Is it like this? Okay. Now that's, I guess that's too much faces, so I'm going to reduce this a little bit using remesh. A bit more. Okay, it might not work at this kind of irregular stuff. Okay, I guess that there's a bit of problem here. Well, let's see how it does. Or I'm just going to use the BDV from Polygon to make it all mushed up. Then convert BDV back to a polygon. Then do the remesh. I can say this 0.05 or 0.02. Maybe like this. Now let's see. There might be a lot of overlaps in this kind of geometry. So, but let's see. And we need to change the switch. Okay, it might take some time to calculate the spanning tree. Let's wait for a while. Okay, it's also taking some time to calculate the folding. Okay, there might be a chance that something is not connected because it stopped at some point. Okay, there might, if there's any island which is separated from some geometry, then this is not going to work. You need to have all the geometry as one connected face. Okay, so I guess I should not use this one, but instead maybe I could use the test pighead. And make it a bit more low res. Okay, I am not sure if it's going to work. Let's see. Okay, well, there is a lot of overlap somewhere around here. So could have some random values applied. this one and see if you can find any options. Doesn't overlaps it. Well, it does overlaps a lot of times. Okay, maybe it doesn't work with the pig head, but the folding still works. You can check how it's going to fold it into a pig like this. So in terms of the visual purpose, I think it's fine, but in terms of the fabrication purpose, maybe you need to have a seam somewhere to cut this into 2 pieces or 3 pieces to avoid the overlaps. It is also mentioned in the blog that I have shown you as it's a reference that some of the meshes cannot be unfolded without overlaps. So okay, let's also try using the remesh of this torus version. It looks a bit regular, does it? Okay, let me change the target size to 0.25 and change this to 3. Okay, so this is how it looks like for the torus. I set it to 1. Now for the torus, maybe I'll be able to find out some optimized position where it doesn't have much overlaps. Maybe I should do somewhere like this. Yeah, I guess in order to find out the best position, we might need to have another feedback loop to search through all these possibilities. And I might need to set the seed to some bigger numbers. Okay, let me go back and see if I am applying the seed correctly. Right, so right here I might need to use n as well. So n multiplied by some value plus t. Okay, well, maybe that's good. Okay, and it goes like this, and create a donut like this. Okay, things work. And you can try various options. Yeah, it's pretty fun indeed. Really, I found it's really fun to explore it. I do like you doing the computational design stuff. This kind of stuff really inspires me a lot. Okay, well, any questions, I can answer it. If not, I would like to end this. is Nori? Why all Houdini tutorials are so long? I don't know. You ask me. For me, I'm explaining everything that I did here, so that's the reason why it becomes so long. I mean, I can just skip all the explanation to make it faster. But is that really what tutorial is about? I don't know. For myself, I want to know every logic behind the scene, so that's the reason I'm explaining every single step that I'm doing here. But maybe in some case you might not like that. In that case, I don't know what to say. Some way to cache the unfolding animation. Yeah, I think so. You could, for example, let me choose a simple geometry like the sphere. Okay, so let's say if I want to create an animation for this one, I can make based on the time frame. Let's set the time frame to something like 30 and then use something like file cache and use the save to disk. Then I can check this load from disk and play it. I can play the unfolding animation like this. Now if you want to make it as open and closed loop, then you can change the expression here. Maybe multiply this by pi, multiply by 2, and use it with the sine wave. For the sine wave we have -1, so I can add by 1 and then multiply by 0.5, then you'll be able to have a wavy value between 0 to 1. And let's save the cache again. And this time you'll be able to, oops. Okay, I think I did something wrong here. I shouldn't use pi, but instead I should use 360 in the expression. Okay, my bad. Well, so you could create like unfolding butterfly with it. Alright, so that was a lot of coding, and I hope you get some out of this. I guess you need to look back if you want to fully understand what's going on here, I guess, because there's especially for creating a spanning tree and unfolding, there's a lot of there's like 2 recursive loops that I have done here, and especially for the unfolding we have like double recursive, one to search for the children and one to do the rotation for each of the face. So that's a lot of complexity here, which I have to admit, but the result you get is pretty nice, I think. Yeah, how is this? Like this. Even though the template looks weird, the animation looks really interesting with this one, doesn't it? How about this one? Alright. And this one. More like a plant, like. Now more faces you have, the rotation calculations will become slower. That's because of the way I have implemented here. So I do believe there's a bit more efficient way to do things that I did here, and also for the spanning tree. Although for the spanning tree, I don't think you need to make it efficient that too much, because in terms of animation you don't use this. But in terms of folding, if you want to make the folding animation, then maybe you might need to make these more efficient. This calculation is more efficient. But I just tried this, just tried to implement this today, so I couldn't really have some time to figure out how I could optimize this one. Maybe if you could do that, and if you find a better way to do this, and if you could tell me, that would be really great. Now, just to mention, I have used the reference from this blog, Unfolding Meshes from the Houdini Gubbins. It shows you a basic algorithm which I have followed. So looking at this one might be enough for some of you who know how to code. If you don't know how to code, then you can look back to the one that I have just done here, because I'm explaining every single step. Okay, so thank you very much for watching. I am going to leave this as an archive, and so that you can watch this later. It's for your reference, and I'm also going to upload the file that I've just created to the GitHub repository, which I'm going to paste the link to the video description page of this video, so you can download the file and see for yourself, see how this works for yourself. Okay. Hopefully it will be useful, or could be used for any of your project. I'll be happy to I'll be really happy if you could use that for any purpose. Yeah. But as I mentioned, all the algorithm credit goes to this guy here, so I just followed his algorithm. Okay, so thank you very much, and would like to end here. And I have the Patreon page myself. You can go there from the video description page if you find the video interesting. If you would like to support me, I'll be really appreciated. Okay. And I'm going to try to do another live like this next week with other topic. might be computational geometry related, or might not, might be something different, but Houdini related and mostly using Vex for all the time. Okay. Thank you, and see you sometime or next week. Alright, and just one thing to mention, I'm also doing the basic series for the Vex to teach you the basics of the Vex, called as a Vex for Algorithmic Design, which you can check in my channel as well, where I'm teaching the basics of Vex from scratch, from attributes to like randomness or noise. The next topic that I'm going to post is about the basics of solver together with the Vex. So if you like to create some kind of animated recursive simulations, then maybe you might want to check that out as well. Okay, so that's it. Thank you, and goodbye, good night.